My next talk is about the Basin-Scale multi-GPU accelerated hydraulic fracture modeling and simulation. So this is the overview of the talk. First, I will give some introduction to motivation, and I will talk about the EDFM AI workflow and application, and also this Basin-Scale field application, which is a huge shale gas reservoir that we apply this workflow, and talk about the summary and future work. So for the motivation here, as we can see here, the US unconventional reservoirs, especially in the Eagle Ford and also in the Bakken, there's already a lot of wells through the past 2 decades. And one question here for the, especially for the investment point of view, is that we need to consider the full-scale reservoir model to better help the investor evaluate the basin-wide asset and evaluate their value of properties. And also for the field-wide calibration, we also have the opportunity to better optimize the future well placement. For example, for the remaining reserve, which part of the reservoir actually has more remaining oil and gas, and we can put future wells, infill wells to those kind of locations. So that leads us to the necessity to model a big scale model. And as we already talked a lot about the GPU, for the power of GPU is, I think it would be the future of the computing, especially in the reservoir simulation realm. And we already seen a lot of applications from the initial purpose. The GPU is built for the gaming purpose. And now we, with all these big AI language model and also data mining, they are also requiring to use a lot of chips and GPU chips. Now, if we compare the number of computing cores, we can see the GPU can achieve thousands of computing cores. And one advantage with the GPU reservoir simulation is about its potential. So if we see this plot, we can see that the GPU performance actually what its future looks like. For example, in this plot, we can see the comparison between the CPU and GPU bandwidth. So for the bandwidth, this is one of the key bottleneck when we talk about the reservoir simulation. So the memory bandwidth, what is this? So this is how fast you can transfer data. For example, your model into the GPU memory. So this actually dominates what is the simulation efficiency for your model. And we can see here throughout the years, the GPU has a kind of big exponential increase for the memory bandwidth compared to more like a linear increase in linear growth when we look at the CPU bandwidth. And for the another key advantage for the GPU is its cost effectiveness. So, for example, a lot of us may not have the access to the HPC. For example, thousands of the CPU computing cores, right? They may just have for example, the gaming laptop. And using just these gaming laptops GPU, we are able to run the reservoir simulation just on your own laptop. And this is a huge advantage regarding the spatial cost using these kind of the technology. So here I listed some of the popular brands regarding the GPU models. And we can see here the price of these GPU is kind of cheap only about a few $1,000s, and you can get a lot of performance out of those. So for example, this 5090, I believe, is one of the most popular NVIDIA gaming graphics card. And we were able to achieve about 1.8 terabytes per second of the data transfer speed for the memory values. And for the memory size, this is related to how big of the model you can consider. So for example, for the 5090, we can consider 12 million grid blocks of a reservoir model size. Okay, so another aspect regarding the GPU reservoir simulation is building the proxy model. Okay, so we have already seen a lot of application in this type of big language model, such as ChatGPT, DeepSeek, etc. And we actually are moving forward to extend this kind of application to more oil and gas industry related models, such as a big scale reservoir proxy model. So we are able to, using the GPU power, we are able to model big scale reservoirs. And after that, we can run hundreds, thousands of cases of these big reservoir models and build the so-called physics-driven proxy model. So this is what we call AI for sciences. And later on, probably in the future, because a lot of robotics are kind of evolving very fast, maybe in the near future, we will also move to kind of like a physical model, physical proxy model, like the robot in reality. This is called the artificial general intelligence. Okay, so next I want to talk about the EDFM AI workflow for the automatic history matching. So, EDFM AI, for this workflow, we are coupling the EDFM reservoir simulator, especially the GPU simulator, and also the AI proxy to help us perform an iterative approach to automate this history matching process. So two of the key AI models that we considered using EDFM AI is the XGBoost with MCMC, which is Markov chain Monte Carlo sampling. So this framework, it works best with a smaller sample size. And we also tried another framework, which is the USMDA. So this framework is really robust for higher number of uncertainties. So when we are moving to consider a big scale reservoir model, the XGBoost, this framework may not perform best compared to the ESMDA. And for the ESMDA, a lot of the big weather model to predict the weather forecast, they also use this algorithm to consider a large number of uncertain parameters. Okay, so this one we already covered, so the next slide. So using this EDFM AI workflow, we are able to move forward to consider multiple shale gas pad models. So we actually apply this workflow to a real world case, which has about 8 shale gas pads, or a total of 22 wells inside this reservoir. And using the EDFM AI workflow with the ESMDA, we are able to capture the history response for all these 22 wells with more than with about 200 hydraulic fractures in this model. And after the calibration, we can see for this best match model, we can see what is the gas in place visualization and also the dynamic pressure visualization. So we can see that this part of the reservoir, amount of remaining gas is kind of large, and we also see that some of the wells, the inter-well area, like between these two wells, they may not have a high degree of drainage, so there are still a lot of remaining gas, the gas saturation high remaining in this reservoir. So this kind of results provides field engineers with insight regarding where to put potential future wells to do the infill well drilling and optimize the production. And then for the next application, we want to go even bigger, right? So this is another big application that we did, modeling a basin scale shale gas reservoir, right? So for this reservoir, we are considering more than hundreds of square kilometers of the total area, and more than several hundred wells in this reservoir. And the number of grid blocks that we used for this reservoir is about 60 million grid blocks. So using for this kind of number, we cannot consider the reservoir model in just one GPU. We need to bundle about 4 GPU together to consider this full field scale reservoir model. And if we bundle these 4 GPU together to do the simulation on this reservoir, with 20 years of production simulation, we are able to finish the simulation only in 2.5 hours. And for this reservoir model, the first thing we did is that we need to construct the basin scale geology model. So here in this model, there are a lot of vertical wells that has those kind of well logs. And the first thing we need to do is to construct the geology model. For the geology model, the whole area here we consider is more than 1,500 square kilometers. And for the grid resolution here, we are able to achieve about 20 meter times 20 meter, and the vertical resolution is about half meter. So this turns out the total grid number here for the original geology model is about 1.2 billion grid blocks, which is orders of magnitude higher than the reservoir model. So one of the future work that SIMTech is also considering is to bundle maybe about 50 GPU together to consider this number of reservoir simulation. So there's no need for any upscaling when we transfer the geology model to the reservoir model. And then for the next step, we also did the geomechanics model, which is built from about 20 vertical well logs. And here we use a little bit larger grid size for the grid resolution, about triple the size of the grid block for the geology model. And the grid number here is also about 15 million. And the third step here for this basin scale reservoir is that we also built the natural fracture network model. So for building the natural fractures, we need to use some of the interpreted data from the seismic response, such as the maximum curvature and also the end tracking. So gathering those data are also very hard. It's about 6 gigabytes of the interpreted data, seismic data that we need to handle. And using some of the automated algorithm that we also developed for the EDFM building, we are able to achieve the natural fracture generation more than 1 million fractures only within 2 hours, that we can build all these basin-wise natural fracture models. And for the natural fractures models, we also calibrated against some of the available data, such as the image log. And we compare the image log data and the well trajectory along with or generate natural fracture to calibrate this natural fracture model. And also for some of the fault that's observed in the field based on the drilling response, the field engineering are able to tell you that some locations there are big scale fault. So we also compared the generated natural fracture with these fault data to further calibrate our natural fracture models. And the next step that we did is that we want to build a so-called proxy model, which is physics-driven fracture proxy model from several of the representative shale gas pads. So here, there are 4 steps when we build this proxy model. So the first step, we need to select the representative pads that has different completion design, different landing zone, and within different sectors. So we cover a lot of data points here. So we choose about 5 representative shale gas pads. And then we use the EDFM AI workflow and also with Zephyr AI, we calibrated what is the wetted geometry and also the effective geometry for all of these pads. So this is the second step. And the third step here is that we want to construct this fracture proxy model. So basically, we are using AI algorithm to learn the relationship between, for example, different stress conditions, different completion design, different cluster spacing, and different sand intensity, fluid intensity, different landing zone. And the target objective function is what is the fracture geometry. We're trying to use the AI to train this model to learn the relationship between the input and output. And then using this proxy model, we are able to apply it to the Basin-Scale reservoir. So for all those hundreds of wells, how can we generate the fractures? We can easily gather those 100 wells input parameters. For example, all those wells, what are their landing layer, what are their completion design, and then using those kind of input with the proxy model, we are able to predict all the 100 wells hydraulic fracture geometries. So this is the first step that we did for this Basin-Scale reservoir. We actually selected based on different sector, different landing zones, and also different completion designs. We were able to select about five representative pads out of all the available 12 pads that we have. And then we continue to build this fracture proxy model. And we actually found there are some trends for this proxy model, the relationship between the input and output. For example, in this landing zone, the number 1 and number 2, the fracture geometry is kind of different than the landing zone 3 and 4. So this zone has a higher fracture length and lower height. And when we looked at the stress condition, we see that there's a stress barrier on top and the bottom of the landing zone 1 and 2. And that corresponds well with the stress observation along with our calibration results. And then we continue to apply this the fracture proxy model to quickly generate all these wells, more than 600 wells hydraulic fractures, which is about 100,000 clusters of hydraulic fractures, and we are able to quickly generate all these fractures within all this basin reservoir. And then we continue to run the reservoir simulation using the 4 GPU bundle, together. And for this one, for this model, we took about 5 hours to finish all the 600 wells simulation. And the key point here we want to look at is one of the key interests from the operator is that they want to further develop this reservoir, but they don't know where to put these future wells. So when we look at both the pressure and the gas saturation distribution after 20 years of production, we see that at this location, there's still a quite high residual gas saturation that the operator should focus on putting more wells around this region. So that's like a big picture of the remaining gas reserve calibration. And then we also did some sensitivity regarding more detailed characterization for the residual gas remaining in reserve. So we look at some of the pads, especially from this reservoir, that has quite high number of remaining gas in reserve, and we see that at different well spacing, what is the remaining gas in reserve that we have for these pads, and we also tried with different infill well spacing scenarios to see which one gives you more recovery using the newer wells, using the infill wells. And lastly, this is the cloud-based reservoir simulation that I also talked about during the demo. So currently, I'm working on developing this cloud-based reservoir simulation, and compared to the Z4RE that you need to install in your own computer, this one you don't need to install at all, and you don't need to get the license. And with just a few clicks on this web page, you are able to build the reservoir model, perform the fast model calibration, and also the production forecast. And we are also able to couple all the fracture models, or you can generate the fracture yourself within this interface. And we already put the EDFM GPU reservoir simulation on this cloud basis. So just to wrap up for the summary and future work, so we believe that the GPU supercomputing is actually the future for the reservoir simulation, and especially with AI algorithms, with GPU computing, we really are able to make fast decisions for the operator to optimize their completion design, their well spacing design, and also their development strategies. And lastly, the Basin-Scale reservoir simulation is key for the asset evaluation, like the total asset if you want to evaluate for, especially for the investors, and also for the field scale optimization. This is one of the key steps. Some of the future work moving forward is that so this model is actually not in the US. This was one model in Asia. And we actually want to build also the big model regarding the shale oil reservoirs in US, such as the Bakken and also the Permian big model. And then moving forward, we also want to experiment with the digital twin concept for the reservoir simulation. So here, this is a pilot test between the reservoir simulation and the digital twin proxy. So we're able to obtain a very similar result between the digital twin proxy and the reservoir simulator. And one of the key advantage for the digital twin is that it only takes about less than 0.01 seconds to get the results instead of minutes. So that's also one of the areas that we want to work, especially work in the near future. So thank you very much for both listening to both of my talks, and now I welcome any questions, comments.